Hello students, in today's class we're going to work on exponential growth and decay. So let's get started. Let's take a quick look at the law of exponential change. It states that if y changes at a rate proportional to the present amount, so dy dt is equal to ky, where k is a constant, and y sub 0 is equal to y naught, then y is equal to y naught e to the kt. Number k is called the rate constant. If k is greater than 0, it's exponential growth. If it's less than 0, it's decay. So let's take a look at a quick example here. It says use separation of variables or differential equations to solve the initial value problem. Indicate the domain over which the solution is valid. So when we're doing this differential equation, what we're really trying to do is separate the dy and the dx. So in order for us to do that, we're going to multiply dx to both sides. That gives us negative 2xy to the second power dx. Notice we want the y's on one side and the x's on the other, so we're going to divide by y squared to both sides. We're going to end up with 1 divided by y squared equals negative 2 dx. Now if we take the antiderivative of both sides, we end up with negative y to the negative first power equal to negative x squared plus c. Now if you take a look at the problem, it says y is equal to 1/4 and x is equal to 1. So what we're going to do is we're going to substitute both values in to find out what c is equal to. So we know 1/4, or 2500 is 1/4 to the negative first power equals negative 1 squared plus c. This turns out to be negative 4 equal to negative 1 plus c. So c is equal to negative 3. And then we could substitute that in to our original, which is negative y to the negative first power equals negative x squared plus negative 3. If we simplify this a little bit further, we end up, if we divide by negative 1 to both sides, we're going to end up with y equal to x squared plus 3. But that y was to the negative first power. So because that's an inverse, we can flip the other side and basically have y equals 1 divided by x squared plus 3. And so first we found the initial value, so we could find c, and now we know that this is the domain. So let's move on. Getting back to our exponential growth and decay, we want to talk about things that are continuously compounded. So in terms of interest, this is something that's compounded continuously. And so what that means is when we look at certain accounts, some things are done, or when banks take your money, every month they compound it. If it's compounded continuously, they're taking your money and compounding it so that it can grow more and more at a faster rate. So we look at that formula, or the formula is defined by a of t equals a sub 0 times e to the rt, where r is the continuous interest rate in decimal form, and t is your time. So, example 1, find how long it would take for an investment to double at a continuous rate, or a continuous 4.9% interest rate. So, we're going to look at this and write it down as a sub 0 equals, or a equals a sub 0 e to the rt. So if we want something to double, we're going to take our initial amount, which is a sub 0, and it's going to double. So 2 times a sub 0 equals a sub 0 times e to the r. In this particular case, your rate is 4.9%, but in decimal form it's 0.049 times t. You'll notice on the left and right side that we both have a sub 0. So if we divide that to both sides, we're left with 2 equals e to the 0.049 t. And in order for us to simplify this, or get rid of the e at least, we're going to need to multiply both sides by ln. So we're going to take the original, multiply by ln, so we'll be left with ln2 equals 0.049t, and if we divide 0.049 on both sides, we end up with 14.146. So if we wanted our amount to double, it would take 14.146 years. So let's take a look at another problem. So a couple wants to have an investment yield of $500,000 when they retire in 12 years. How much do they need to invest if their expected continuous interest rate is 5.7%? So again, if we start off with our A equals A sub 0 times e to the kt, we know that at the end of this 12 years, they want their money to be $500,000. We don't know what their initial amount is, so we're going to keep that as A sub 0 times e to the k, their interest rate is 0.057%, times 12, because they want to keep it in there for 12 years. Now, if we just want to solve for A sub 0, we're essentially just dividing the e to the 0.057 times 12 to both sides. So we're left with 500,000 divided by e to the 0.057 times 12. And when you type this up in your calculator, you end up with $252,297.29. So this is the initial amount that they need to invest if they want to keep it in there for 12 years. So another thing we want to look at is decay. We've looked at exponential growth, now we're going to look at decay. And one of the ways that this works is through radioactivity. Now, some elements or isotopes of elements are unstable and over time convert to a different element or isotope. These elements or isotopes are called radioactive and go through radioactive decay. So the amount of radioactive substance is defined by y of t equals y naught or y sub 0 times e to the negative kt. Again, negative because we want it to be decay. The half-life is the time required for half of the sample to decay, hence half-life. Now, half-life, or tau, which is this little t that you see here with a squiggle at the end, or half of a pi sign, is the time required for half of the radioactive sample to decay. So we look at tau equals ln2 divided by k, and we know that that k is equal to ln2 divided by tau. Now if we take our original formula, which is right here, and we make the substitution, we get y of t equals y sub 0 times 2 to the negative t divided by tau. Now, notice because it's half-life, we want that 2 in there. That negative exponent that we're seeing here, if we applied it, we'll turn this 2 into a 1/2. So let's look at some problems to make this a little bit easier to see. So a clay pot was found to have 83% of its original carbon-14. Estimate the age of the clay pot. The half-life of carbon-14 is approximately 5,730 years. So, first thing we're going to do here is we're going to start off with our formula. So y equals y sub 0 times e to the negative t divided by tau. So for the interest of this, I'm just going to write tau. Now, we found that the pot has 83% of its original carbon. So we want to know, since we're talking about decay, the opposite. We don't want to know how much is left over, we want to know how much it decayed. So in this particular case, it's 0.17% of the original. So for our y, we're going to write 0.17 times y naught, because it's 0.17 or 17% of the original that was decayed, equals y sub 0 e to the negative t, because we don't know how many years it's been around, divided by 5,730, because we know that's the half-life. So if we divide y sub 0 to both sides, we get 0.17 equals e to the negative t divided by 5,730. Now if we multiply by ln to both sides, we get the following. And if we multiply negative 5,730 to both sides, we get 14,648.13 years old. So that pot is 14,648 years old. So hopefully that helps. Let's try another one. So the half-life of the radioactive element plutonium-239 is 25,000 years. A rock was found containing 1.8 grams of plutonium-239. Based on the mass and composition of the rock, a geologist concluded that it originally had 9.3 grams of plutonium-239. How old is the rock? So, for this particular case, we're going to look at what we have. Now, starting again with our original, we had y equals y sub 0 times 2 to the negative t divided by tau. We know that this originally started off, or this final rock has 1.8 grams. We know that it originally had 9.3 grams times 2 to the negative t divided by 25,000. Now we're going to divide 9.3 to both sides. We're going to get 1.8 divided by 9.3 equals 2 to the negative t divided by 25,000. If we natural log both sides, we're left with the following. Now if we multiply by negative 25,000 both sides, oh, sorry. When we multiply by ln to both sides, I forgot to write the ln here. So let's start back from the top. From here, we would have been left with ln here, ln 1.8 divided by 9.3 equals negative t divided by 25,000 ln 2. And if we divide ln 2 to both sides, we're left with ln 1.8 divided by 9.3 divided by ln 2 equals negative t divided by 25,000. If we multiply negative 25,000 to both sides, we get t is equal to 59,230 years old. So years old. So last thing I want to look at is Newton's law of cooling. So Newton's law of cooling is important because it helps us, especially in forensics. Now it says the rate at which an object cools or warms is proportional to the difference between its temperature T and the temperature of its surroundings. So in forensics, this is how they figure out how long, for example, a body has been dead for. They look at the surrounding temperature, they look at the temperature of the body, and they're able to calculate how long this person has been deceased for. So let's look at this example. A hot cup of coffee is 54 degrees when it is poured. It is left sitting in room temperature with an air temperature of 22 degrees Celsius. After 5 minutes, it is cooled to 42 degrees Celsius. How much longer will it take for the coffee to reach 37 degrees? So a couple things we want to note here. We know that the initial temperature is equal to 54 degrees. We know the temperature of the surroundings is equal to 22 degrees. We know the time is 5 minutes. And we know that the final temperature is 42 degrees. So notice how we just started off with what we know, and now we're going to look into the formula. So we know that T, or T final, is equal to T sub S plus T sub 0, the initial temperature, minus T of the surrounding, times e to the negative kT. So we know what the final is. The final is 42. We know the surrounding is 22. We know that it started at 54 and its surrounding is 22 times e to the negative k times 5, because it was 5 minutes. Doing some math, we subtract 22 to both sides, we get 20 equals 32 e to the negative 5k. We're going to divide by 32 to both sides. So e to the negative 5k. We're going to ln both sides. And notice ln and e cancel each other out. And we're left with 5k, negative 5k. So k is equal to ln 20 divided by 32 divided by negative 5. So k turns out to be equal to 0.094. Now that we have that constant k, we know that that's the constant at which it cools off at. So the real question is, how much longer will it take for the coffee to reach 37 degrees? So if we start off with our initial formula, we know that we don't know what the T final is. That's what we're trying to figure out. We know what the T surrounding is, which is 22. We know it started at 54 minus 22 e to the negative 0.094 t. Actually, my apologies. We do know what the final is. We wanted the final to be 37 degrees. So we're going to subtract 22 to both sides. We're going to get 15 equals 32 times e to the negative 0.094 times t. We're going to divide by 32 to both sides. Equals e to the negative 0.094 t. ln both sides. We know that ln and e cancel out, so you're left with negative 0.094 t. We're going to divide negative 0.094 to both sides. We get ln of 15/30 seconds divided by negative 0.094. And finally, it turns out that this is 8 minutes. That means it'll take 8 minutes to cool from 54 degrees to 37 degrees. Notice the question said, how much longer will it take to reach 37 degrees? Well, if we're looking at from the when it cooled down after 5 minutes, it'll take an additional 3. But it'll take 8 minutes total to cool down. So that's all for now. I'll see you guys next time.